Hello everyone, my name is Monica Rue and I'm a data engineer at IOMED. At IOMED we develop natural language processing algorithms to structure clinical notes. In this way, by structuring clinical notes, we are able to query the information that these notes contain with the main goal of accelerating clinical research. We use OHDSI Common Data Model as our data model, and today we are happy to share with you an extension that we designed to store the output of NLP pipelines. So as you know, a lot of data is generated at hospitals every day. Close to 80% of this data is non-structured and a large part of it is free text. NLP solutions are able to extract and encode relevant medical concepts from free text. These NLP algorithms take into account complex context, such as negations, family or personal backgrounds, or past events. This is the main reason why NLP solutions are becoming more and more common to structure all this data, especially in the context of clinical research. So as I said before, NLP systems are able to detect entities, for example, pain, and their context. For example, he had no pain last week. In addition to entity detection, there are many other NLP tasks that can be performed on text, for example, translation, grammatical error correction, etc. Additionally, since what NLP systems detect are probabilistic data, it is very important to store the traceability of the data. For example, the version of the algorithm and the number of iterations. All of this makes the output of NLP pipelines very complex. The OHDSI Common Data Model is a great schema for storing structured data, but although it provides a specific table to store the output of NLP algorithms, the NoteNLP table, it's quite limited for all the output that NLP pipelines can generate. The NoteNLP table focuses mainly on entity recognition, and the metadata about these entities, for example the temporality, is stored as free text, which makes querying this table very difficult. In order to store all the output of the NLP pipelines, we extended the OHDSI Common Data Model with our own NLP schema. This schema, as you can see, is made up of 11 tables, which allow us not only to store the NLP pipeline's output, but also the metadata about the machine learning models used to process the clinical notes. These tables are divided in two main groups: tables which store information detected by the NLP systems in spans of notes, and another group of tables which store information about the NLP pipelines that have been run. So, on the one hand, linked to the OHDSI Common Data Model node table, we have the node span table. This table stores references to parts of the text, which can be just a word, a sentence, or even the whole node. Linked to this, we have the node span concept table, which stores the related concept ID of each span of text. On the other hand, we have the node span relationship table, which stores relationships between spans of text, and two specific tables to store additional information on date and quantity entities, NLP date table and the NLP quantity table. On the other hand, we have a set of tables to store information about the NLP pipelines. To sum up, the NLP execution table stores information about the NLP execution, the node span, and its related information has been obtained with. This table is related to the NLP system table and the pipeline table, which store more detailed information about the components of the NLP execution. This schema makes it easier to query the stored data. For example, if we want to retrieve all nodes where a certain condition, for example of psoriasis, was stated, would involve a joint query to the node span concept, and finally concept table, filtering by the concept ID of psoriasis. If we also want to know those nodes where psoriasis was not only stated but also present and detected as a primary diagnosis, we would add to our query the concept ID of primary diagnosis and organic disease present. We have installed our platform in 5 hospitals in Spain so far, where we have not only transformed their data to the OHDSI Common Data Model, but also processed all their clinical notes and stored the output in our NLP schema. Our tools have processed more than 70 million clinical notes so far of more than 4 million patients. We are currently taking part in 8 clinical studies with both structure and NLP data, and thanks to having this clinical notes structure, we make it easier for hospitals to take part in OHDSI studies with both structure and data from clinical notes. So as an example of the power of a structure and NLP approach, we analyze the prevalence of 4 dermatological diseases: atopic dermatitis, chronic urticaria, hidradenitis, and psoriasis. In the image, in this slide, you can see the number of patients detected per disease and extraction method. We divide each graph into patients found via structure diagnosis, that is, diagnosis in the condition occurrence table, and via NLP. And as you can see, there are many more patients detected by NLP than by structure diagnosis. The main problem with the NLP pipelines is the huge amount of data they can generate. Here you can find the average number of notes and concepts detected per note in each hospital. And as you can see, the output volume is extremely high. We have on average 12 million notes per hospital, and we detect 200 concepts per note on average. So we have introduced a new extension to the OMOP Common Data Model able to store the output of NLP pipelines. This schema has already been successfully tested in several production environments and has already been presented to the OHDSI NLP Working Group. As a future work, we are working on normalizing and optimizing this schema since, as I already mentioned, the output volume of these NLP pipelines is extremely high. So thank you very much for your attention, and we will be more than happy to answer any questions you might have. Ciao!